Okay, this is Chapter 8, Kinetics and Equilibrium, Lesson 2. Our goal is today to understand potential energy diagrams. We're specifically going to focus on endothermic potential energy diagrams and using Table I in the chemistry reference tables. So let's get started. What is a potential energy diagram? Well, first we need to recall we have talked about chemical bonds having stored energy. That stored energy is called potential energy. For that reason, chemists use diagrams called potential energy diagrams so that they can show how the potential energy changes that take place during a specific chemical reaction. So let's recall. A reaction is the breaking and reforming of bonds. So here, A and B have to break bonds in order for C and D to form. The heat of the reaction, also known as delta H, is the amount of heat energy lost or gained throughout a reaction. So it's a change in what's called enthalpy, capital H, enthalpy meaning energy, that's what the word enthalpy means, and the capital H is there for heat. How do we calculate it? It's the heat of the products minus the heat of the reactants, okay? And when we talk about heat, we're talking about potential energy. So it's the potential energy of the products minus the potential energy of the reactants. This is something that you need to know. It's not something that's written on your reference table. Let's recall two different types of reactions that we've talked about so far this year. We have those reactions that release energy and are called, hopefully you're saying it, exothermic. And in an exothermic reaction, our delta H is going to wind up to be negative. And you'll see that when we go through some examples. So energy is on the right. So if I'm looking at a reaction, here's going to be my energy value, and it's often displayed as a number. 26 kilojoules would be perhaps what you would see. Example, sodium and water. If I take sodium metal and put it in lots of water, remember the video I showed you about how group 1 metals react in water. They're very explosive. There's usually lots of heat and fire. So the heat is a product, okay? Whenever we do a reaction, sometimes you'll feel some certain test tubes get warm. That's because they're releasing energy. Reactions that tend to absorb or gain energy, recall, are endothermic. Exo meaning out, endo meaning in. There's our prefixes that we were talking about a couple of weeks ago. Your delta H is going to have a positive value, and your energy is often on the left side of the equation, and it's either written as the word energy, it could even be written as the word heat, or it will have a numerical value. And the same thing on the right. You can have heat, the word heat here too. An example that you can relate to every day is baking, okay? If I want to bake a cake, okay, the batter has to absorb heat in order for the reaction to take place. So we need an oven to supply heat. Okay. Before we look at potential energy diagrams, I want to talk a little bit about Table I on your reference table. It tells us if a particular reaction is exo or endothermic based on the sign of delta H. Remember that a positive delta H equals endothermic, meaning energy is being absorbed, and a negative delta H equals exothermic. And I want to draw your attention to to the bottom of the graph. There is an asterisk on your reference table that says the delta H values are based on molar quantities represented in the equation. A minus sign indicates an exothermic reaction. So if you forget, it is written there, you just have to remember to look. So this is I copied this right out of your reference table. Let's look at a couple of examples so we can understand how this works, and I'm going to tell you what types of variation and questions you might see on the Regents exam. So we're looking at N2 plus 2O2 yields 2NO2. All right, we're looking at this one right here. N2 plus 2O2 yields 2NO2. So when you look at that, you'll see that there is a positive 66.4 kilojoules. So I'm going to write that here, positive 66.4 kilojoules. That's N2 plus 2O2 yields 2NO2 gas. Notice that delta H is always kilojoules per mole. So this, it doesn't say mole, but the asterisk tells you that it's a molar quantity. So for one, or whatever is in the reaction. So in this example, you're producing 2 moles of NO2, and you need to absorb 66.4 kilojoules in order for the reaction to take place. So this is going to be endothermic. Let's look at a different one. N2 plus 3H2. So N2 plus 3H2. Here we go. N2 plus 3H2 yields 2NH3. That's a negative 91.8 kilojoules per mole, and that tells us that it's exothermic because it has a negative sign. And the last one that we're going to look at is the reverse of this reaction. So now it's telling us 2NH3, so this is actually the reverse of number 2. When the reaction is reversed, you won't see it in the reference table, but you have to realize that the reverse reaction, all you're going to do is flip the sign. So this is going to be a positive 91.8, because here, to form NH3, we released 91.8 kilojoules of energy per mole. Now to break bonds, remember, a window doesn't break by itself. We need energy. Energy has to be absorbed for it to break. This makes sense that we're going to absorb 91.8 kilojoules per mole in order to break the bonds. Now, one thing that I want to point out while we're here on table I. Let's go back to number 1. N2 plus 2O2 yields 2NO2 gas. We said that this was a positive 66.4 kilojoules per mole. This amount of energy is absorbed when 2 moles of gas are produced. So I could ask you the question, how much energy is absorbed when 1 mole of gas is produced? Now you can do it intuitively and say, well, if 2 moles produces this, then 1 mole would produce half of that. So 1 NO2 gas being formed would need positive 33.2 kilojoules per mole. But maybe it's not so obvious, so you can always set up a proportion. 2 moles NO2 to 66.4 kilojoules, and 1 mole of NO2 is how many kilojoules? So you can set it up that way too. And when the Regents ask you about this, honestly, they normally don't ask a straight question. They usually vary the number of moles. Okay. The forward reaction, as it's called, is reading left to right. So the reaction moves to the right. So here we have A plus B forming C plus D. This is considered a forward reaction. If we're reading right to left in a reaction, then the reaction moves to the left. So if it's C plus D is forming A plus B, this is the reverse reaction. Activation energy is the amount of energy needed to get a reaction started, to form the activated complex. Remember, I mentioned that the activated complex is an intermediate place where reactants are breaking and reforming bonds. This is a very unstable place, and it is temporary. Okay. So you must get over the bump, so to speak, in order for a reaction to be successful. So you have to get to the top of the hill before you can go down the other side. Let's look at what we're talking about. This is an exothermic potential energy diagram. And I'll explain why. Here's typically where our reactants are. Here's typically where our products are. It's exothermic because it is going downhill. Remember our downhill heating curve? It was exothermic. Well, this is our downhill potential energy diagram. So this is releasing energy. And you know it because the products are lower than the reactants. This side of your graph is usually energy or potential energy. And that's usually measured in kilojoules. And this down here is time. It can be measured in seconds, minutes, depending on what you want to measure it in. This is the activated complex that we spoke about. And from here to the top of this hill, that is our EA. This EA equals activation, or energy of activation. We call it activation energy. It's the amount of energy needed by the reactants to get to the top of the activated complex, that intermediate place where bonds are breaking and reforming. Now, how does a catalyst shorten the reaction time needed for a reaction to complete? Well, the activated complex gets lower, which also lowers the activation energy needed for the reaction to occur. So right here, this is with a catalyst. Notice now my activation energy with the catalyst is only this much, which is like less than half of what it was without the catalyst, without the catalyst. So this one, let's label this. This is without catalyst. And this one is with catalyst. So it creates an alternate pathway for the reaction to proceed with less energy. Therefore, it reduces the time. I mean, think about it. How long does it take you to ride your bike to the top of a huge hill as compared to how long it takes you to ride your bike to the top of a very small hill? Endothermic potential energy diagrams. Remember, they have a positive delta H. So the product side, which is on the right, that's right here, is always higher than the reactant side, which is on the left, which is right here, meaning that energy is absorbed. Now, I'm going to explain the difference very quickly. Let's say okay, let's just for argument's sake say this is 0, this is 10, each increment is 10. Delta H is equal to basically the H of the products minus the H of the reactants. So my products are at 10, 20, let's see where this line is. Let me go across here, if I can get a straight line. All right, let's say it's about halfway. So this is 0, 10, 20, 30, 40. This is 35. So it's going to be delta H is equal to 35 minus where the reactants are, 10. So my delta H is equal to 25 kilojoules. This is a positive value, okay? If I did this, let's say this was an exothermic curve like the one we just looked at, and let's say this is 0, okay, and let's say this is 40, and that's about 20. So for this one, remember, delta H is equal to products, which is 20, minus reactants, which is 40. So my delta H is going to be negative 20 kilojoules. So this shows you right here very nicely how delta H for an endothermic curve uphill, I'm absorbing energy, is always going to be positive because the products are higher than the reactants. But in an exothermic curve, my delta H is always going to be negative because the products are lower than the reactants, and we're always doing P minus R. P comes before R in the alphabet. Okay. Now they want us to label a bunch of things on this diagram. So I'm going to label them on this one. It's the same diagram that you just had. They want us to label the potential energy of the reactants. So I'm going to draw arrows corresponding to the letter. So the potential energy of the reactants, remember this is potential energy on the y-axis. So this value from the reaction pathway to the reactant line is A. This value is the potential energy of the reactants. From the reaction pathway to the products is going to be the potential energy of the products, or B. The potential energy of the activated complex goes from the reaction pathway all the way up to the top. This is C. The activation energy of the forward reaction, I showed you that before. Activation energy goes from the reactant line to the top of the activated complex. Oh, I labeled this EA, sorry. This is D. The activation of the reverse reaction. So remember, forward I'm reading left to right, reverse I'm reading right to left. So from this line, which is really the product line, which would be considered our reactants if it was the reverse reaction, is going to be the EA of, so this is EA of forward, This is EA of reverse, and this would be letter E. And the heat of the reaction is the difference between the products. So I'm going to draw a dotted line because you would have to read these values off your graph. So there's my products. Down here is my reactants. So the difference between products and reactants right here, this is my delta H or letter F. The activated complex is the highest energy point of the reaction. This is where full rearrangement of reactants occur because bonds are being broken and new bonds are being formed. Remember, this must happen for the reaction to be successful, along with proper orientation. So you have to have the activation energy, orientation, which is bond angle, and activation energy, EA. In order to get to this activated complex, these are the two things that you need. Okay, that's it for today. Have a great day.